In the late 1970s, two seismic shifts reshaped our understanding of life on Earth. First, dinosaurs. No longer seen as slow-moving, cold-blooded brutes, they were reimagined as fast, agile predators. Creatures like the Allosaurus, built not just for power, but for speed. The second realization was even deeper in time. The discovery of the earliest complex life forms as they emerged in Earth's oceans around 541 million years ago. And for nearly 200 million years, they remained there, alien and strange.
In modern organisms, when we're looking at them and deciding who's related to whom, we don't just look at the features of the hard parts, we also pay a lot of attention to the soft parts. And very often in the fossil record, that's completely absent. But very occasionally, due to special circumstances, and there can be a variety of these circumstances, not just the hard parts are preserved, and the soft parts are preserved alongside.
Now, thanks to a handful of rare soft-bodied fossil deposits known as Lagerstätten, we can see these forgotten worlds in vivid detail. These sites preserve entire ecosystems. Creatures swimming, feeding, even molting. A moment in deep time, frozen in stone.
My former colleague, Dolph Seilacher, who invented the term, or came up with the term, or I should say applied the German term Lagerstätten to these exceptional preservations, when he started out working on this stuff, he was a bit iffy about whether they would contribute major insights to paleontology, but after a while he came to realize that they really were going to be, critical to understanding the history of life on the planet.
This is the story of how 3 generations of paleontologists, in collaboration with amateur fossil collectors, uncovered the hidden history of early life. How they not only found and decoded these ancient clues, but preserved them for the future, safeguarding them in museums for generations to come.
The fossils that we collect and are of significance, like what we're doing here today, are really the evidence. That is the basic foundation of everything that we do in science. They are the real deal. The rocks and the fossils tell us everything we need to know. And from there, we can hypothesize about how things may have been, what things may have looked like, how animals may have acted. But really, it's the fossil evidence that's the basis for all of that. And that evidence has to be kept in solid care for future generations in perpetuity. And that's really what museum collections are supposed to do.
It is also the story of 4 of North America's oldest Lagerstätten, how they were discovered, excavated, and revealed some of the strangest and most alien creatures ever to exist on this planet.
I'm Ron Meyer. In the mid-1950s, my friend Jerry Gunderson and I began collecting fossils. And for the next 63 years, we collected fossils at many sites throughout the United States and Canada. However, on 4 separate occasions, we either discovered or collected in sites with extreme preservation, excellent preservation, known as Lagerstätten.
Recently, Ron decided it was time to move his unique fossil collection to a museum where they would become available for the scientific community. In 2025, Dr. Brenda Hunda from the Cincinnati Museum Center arrived at Ron's home in Colorado. Her mission? To pack up and transport his fossil collections back to the Cincinnati Museum. Brenda wasn't alone. She was joined by her former mentor, Dr. Nigel Hughes, under whom she earned her PhD.
It's nice to meet
Hugger.
you. Yes, that's
Are you ready
right.
to get some fossils? And
Oh, absolutely.
okay.
Absolutely.
So we're eating a little breakfast now, and then we'll go down.
Okay.
We'll make a plan while we're eating.
Okay, sounds good. Let's go.
Okay, after you. Yep. Yeah.
Also assisting were 3 junior paleontologist enthusiasts, Brooke and Elizabeth, and Brenda's own daughter, Annecy. To introduce the team to the project, Ron had set aside several stray fossils in his garage. Together, they helped decide which specimens should make the journey to the museum and which should stay behind.
Stuff from this trilobite head here.
Yeah, I definitely think this is stuff that
Yes.
should come back.
You want it?
Part of it is
Okay.
going to be that we can unpack it and sort of explore it a bit more at the museum and see what we can find over there. Yeah, because we never know what we're going to find, right?
Yeah.
What is that?
I don't know what that is. Yeah, looks like a bug, but yeah. What do you think,
What do you
guys?
I think we should take it back.
Yeah.
Has some pretty cool specimens in here.
Here's a sneaky little somebody.
Throughout the day, the collections team carefully wrapped and boxed thousands of fossils, each one a window into ancient life. They carried them up the basement stairs step by step, and finally loaded them into the museum's transport vehicle for the journey back to Cincinnati.
So having a collection that consists of these 4 different Lagerstätten for us is a real exciting and very significant part of what we do in the museum, in that we can showcase those materials, put them out for the public to see, and also be a site of exceptional research for scientists from around the country and around the world.
These have become, in the last 30, 40 years, real foci of paleontological research. Because although there are very few of them, they give us this unprecedented look and glimpse into what the biodiversity was at the time that these Conservat Lagerstätten were forming.
The most important fossils Ron and Jerry collected were from the Brandon Bridge Lagerstätte in Waukesha, Wisconsin. Considered, at the time of discovery, the second most important soft-bodied fossil site after the legendary Burgess Shale Lagerstätte.
In 2020, a number of publications came out describing the Brandon Bridge fossil site, and as a result, public television became interested in doing a story on it. And one of the producers contacted me and asked me if I would be willing to go on camera and describe how we made the discovery, which I did do. Back in the early 80s, Jerry and I collected bottles, and we went into a fellow collector who was with the Wisconsin Geological Survey, and he showed us a slab like this full of trilobites, and it blew our mind. And we said, "Where did you get that?" And he said, "Oh, we were on a field trip to this quarry in Waukesha." He said, "There are a lot of slabs like that." So, man, we were motivated because we've never seen anything like that, particularly in the Silurian. So the next weekend we were off to this quarry. We drove up. It was a really large quarry. But we introduced ourselves to the foreman and said, "Hey, we wonder if there's any fossils." Somebody told us about these trilobites, and he said, "Let me show you where they are. It's a bench." So we got up on that bench, and we certainly started finding trilobites. It was very exciting. But then I was sitting there, and there was this very thin layer of rock that was largely dark and had varving, which are little lines would indicate that it had been set down in multiple times, and it split. And I opened it up, and I saw this animal, which we call the halgramite animal. And it was a beautiful, soft-bodied creature that nobody had ever seen before. And I said, "Jerry, come over here quickly." And he said, "Oh my God, this is amazingly significant. We got to collect this site." And so we began the process of collecting that ledge for probably almost a whole year. We go there, get rocks, split them. We'd have to take them into our basement, freeze and thaw them, put them in water, freeze and thaw them multiple times. and then they would split, and we used a fillet knife to separate the layers, expose these incredible animals, and then Jerry would back them up, and you'd put epoxy on them like this to stabilize them, and that's how we collected.
The animals Ron and Jerry found were bizarre, alien almost, and they all lived in the ocean. But just how strange were they? That was the question. Were they as strange as the surreal creatures first encountered in the most famous Lagerstätte of all, the Cambrian Burgess Shale animals? Dr. Derek Briggs is one of the two young British paleontologists that took on the task of describing the Burgess Shale biota, a biota that had been hidden away in drawers for nearly 100 years.
My fieldwork as a graduate student was entirely in the drawers in the Smithsonian. And I mean, that story, of course, was told by Steve Gould in his wonderful life book. So we were literally pulling drawers. And in those days, it wasn't terribly well catalogued. And Fred Collier, who was the collections manager, was very generous in allowing us to basically, rummage around and see what we could find.
Eventually, word spread. There was another rock bench on the far side of the Waukesha quarry, one that might contain more soft-bodied fossils. A new expedition was quickly assembled. A crew from the University of Wisconsin, joined by other paleontologists, including Dr. Derek Briggs, met up with Jerry and Ron. Together, they gathered as many promising slabs as they could, loading them into Ron's truck for the meticulous freezing and thawing technique. What those slabs revealed would mark the end of an era, the last soft-bodied fossils ever recovered from the Brandon Bridge Lagerstätte.
Well, I mean, it was clearly exciting. And of course, in those days, there wasn't a great deal in terms of soft tissues known from the Silurian. So in that sense, it was very interesting. And there was the material is interesting in its preservation, as you well know. It has muscle tissue preserved, which is real soft parts. So in that sense, it was inevitable that we would get excited about it. But progress, as you know only too well, was somewhat slow. I mean, we wrote these two, I'd call them announcements, one which we published in Science in '85, and a second one which was part of a meeting on Conservat Lagerstätten, exceptional preservations, which Whittington and Conway Morris organized in London. And that was also published in 1985, and that was a slightly more extensive account of the biota.
One person who took up the task of describing and publishing some of the animals from the Brandon Bridge Lagerstätte was Chris Gass. He described his reaction to seeing the Brandon Bridge biota for the first time.
The biota was just otherworldly. It was definitely a thing of beauty to me, to see not just one, but multiple exceptionally preserved fossils coming from a site in Wisconsin that was always thought just to have a typical shelly biota. And here we have a fantastic, full-fledged Conservat Lagerstätte.
After Jerry and I finished collecting and preparing the fossils from the Brandon Bridge, we sat down and talked about what was the most amazing thing about the fossils we had just collected. And we realized that we had actually been able to get a look into what all of the animals were there in one living system. Usually we only collected in about 20% of the animals. The other 80% has never shown up. So the diversity of animals that actually showed up blew our minds.
Up until the 1980s, when it was first discovered, there was very, very little material of the Silurian age that preserved soft parts, internal organs and eyes and legs and things like that. And this presented so much information about animals that you don't see in the fossil record. And so we're not even sure if they existed in those places at that time. So Waukesha showed the presence of these different things, different kinds of worms, different kinds of arthropods, other soft-bodied animals that escape preservation, and so many of them. We have sponges, there are microbes in the forms of biofilms and some thin biomats.
The importance and sheer abundance of worms from the Cambrian through the Silurian periods cannot be overstated, like these found in the Brandon Bridge Lagerstätten. These soft-bodied pioneers, whether burrowing through ancient seabeds or drifting through prehistoric waters, laid the foundation for complex life. Their forms were nature's first great experiment, testing the body plans that would one day give rise to fish, and eventually even us.
There were actually a lot of different kinds of worms that were found at the Waukesha biota, not just the thing that looked like a leech but wasn't. There was this thing called a paleoscalicid, which was the most common type of worm from the Waukesha, and also polychaete worms. There are different kinds of polychaete worms, bristle worms, that are found at the Waukesha, and then some other ones that are sort of nondescript. Not a whole lot of diagnostic features on them to really say what they were, but they're annulated types of worms.
Again, from the Cambrian through the Silurian, arthropods with their jointed legs, hard exoskeletons, exploded in diversity and number, becoming the most visible and successful creatures in Earth's early oceans.
One of the arthropods from the Waukesha are the phyllocarids, and there are 3 different kinds of those. All of those were described previously from other locations of the Silurian, and those are arthropods that had 2 shells. They were bivalved. They had 2 shells that covered the front and top part of the body. Generally, there were legs that would extend from the openings below the animal, and then a tail portion coming out the back. Normally, it's much more commonly that the carapace gets preserved without the rest of it. But in the case of Waukesha, many of the specimens were complete. There's one kind of an arthropod, and we're reasonably sure it's an arthropod, kind of tagged the name butterfly animal. I think that's what Jerry and Ron came up with. For the lack of a better word, it has 2 wing-like extensions coming out from the side, and it had a little segmentation going along what would be possibly considered the abdomen, and a head region that looked like it had a pair of eyes. And it was a very bizarre-looking animal. And in fact, Stephen Jay Gould even mentioned that in his book Wonderful Life, as a matter of fact, as being something very odd, sort of reminiscent of the Burgess Shale. There's one other kind of animal that really isn't an arthropod, we don't think. We believe it's a lobopodian. At first, when it was first described, it looks worm-like, and it has little feet on each annulation, but it doesn't have any jointed legs like an arthropod would have. But it's a very, very unusual thing to find something that's soft, again, that's preserved. And of course, Waukesha is the place to go if you want to find that kind of preservation.
Whatever these animals are, Dr. Briggs has been working on describing them for over 20 years. But to date, the most important discovery made by Ron and Jerry from the Brandon Bridge site remains one of the great revelations of the Paleozoic seas: the body, yes, the actual body, of a creature long known only through microscopic fragments like these. A mystery that haunted paleontologists for more than a century. For generations, the term conodont referred only to the tiny tooth-like structures. No one knew what kind of animal made them. Then in 1987, Dr. Derek Briggs was able to describe the earliest conodont animal in the fossil record. And years later, paleontologist Dr. Paul Smith refined that picture.
By the time we got to the 1970s, they'd been assigned to virtually every animal phylum by somebody or other. The phylum is the highest level group of animals. And some people had even said that they were algae. And what we really needed to understand conodont biology was something closer to the evolutionary origin of conodonts. And Derek was working with Don Mikulik and Johan Klusendorf on material from the Waukesha. And in amongst this, Derek's eye was sort of attuned by this time. He spotted what could only be a conodont, and it turned out to be a much more primitive one. So that we still only have around a dozen specimens of conodonts after all these years. And that's why Waukesha is so important.
As you can see from the images in Dr. Briggs' paper, the conodont animal itself is elongated, with a notochord-like structure running through its central body. And clearly, a tooth-like assemblage was found within the head area.
The traditional story, pick up a textbook, children's book from the 1950s, 60s, 70s, 80s, and the story that's in there is that the earliest vertebrates, the earliest members of our evolutionary group, were heavily armored, sluggish, bottom-feeding animals that were going along the seabed and hoovering up sediment and organisms and food. And conodonts present a completely different picture. Conodonts show that at least some vertebrates were highly agile predators, and they were what we call macrophagous. They were eating whole organisms, not just bits of organic material. So these things, in simple terms, were hunting in the water column. And whereas we only have a few tens of species of these heavily armored things, there are thousands of species of Cambrian and Ordovician conodonts. So actually, the dominant vertebrates of those early oceans were predators. They were conodonts.
All the soft-bodied fossils we found ended up at the University of Wisconsin Geology Museum. However, there were a bunch of trilobites that were found as well that were not soft-bodied. And I love trilobites. So I decided I would keep a representative group of these trilobites for my own collection. But now, the time had come to send that collection to the Cincinnati Museum as well.
All right, are you ready, Brenda, to see the
Super excited.
see all the goodies that are about to
For
come?
this for months.
Yeah.
Hi.
Hi.
So what I put out here is the world's largest collection of trilobites from the famous Waukesha Brandon Ridge Formation. And why don't you tell her what you see? Because you guys are the trilobite experts. Remember, they're kind of ghosty, so you have to look carefully. Okay, go
So
ahead.
I think we're seeing a little feast over here. We got some,
Oh, beautiful.
yeah, we got these sets here with the beer flats and then individual specimens in these trays over
Okay,
here.
wonderful.
And here's the Brandon
Oh, my
Bridge.
goodness.
So as a curator, you must be pretty excited. I'd say.
Beautiful, yes. Very exciting.
So these are fantastic trilobite fossils, and the exoskeleton is preserved, but also in this locality we've got the soft tissues. But there's a strange thing about some of these in that the exoskeleton is dissolving away. So you get this kind of ghost-like appearance of these things.
I've never seen that type of preservation before.
Yeah, it's odd, and sometimes it looks like there's kind of like a little footprint, ghostly footprint of things.
Yeah.
So this is Waukesha aspis etona, named after Carrie Eaton from the museum in the University of Wisconsin at Madison. And look at these fantastic specimens. Maybe there's some trace of gut.
Could there? Wow, yeah, right there.
That is in there. And we've got lots of lots of specimens of that form, but it's not only this trilobite. Of course, in a very diverse collection like this, we find other things. So we've got a fantastic harpy
Oh,
here
there he is. Yeah, look
with
at how
the
beautiful.
huge brim around the rest of the head.
Do you think, Nigel, that any of these that have these, the sort of the carbon imprints of possibly the alimentary canal can be micro CT scanned or anything to see if there's anything going on in there?
Maybe, and there's been a lot of stuff on gut contents and
Yes.
things that's been done recently.
As Brenda's well aware, and Nigel, of course, there are various papers out there on trilobite guts and what we can learn from them. And I think new examples might well reveal something which could be interesting, particularly with the kinds of techniques you're describing, because we don't know a whole lot about what they were eating and whether they varied from taxon to taxon. But you've got the experts there with you, Ron, so...
There's one in particular that was just named. We just named it last year. In fact, a fellow named Enrique Rendolfe and I wrote up this trilobite that's the most common one from the Waukesha. And that is so abundant and so distinctive that it was obviously going to be the first trilobite that we would be writing up.
Do you think at this site, Nigel, like the diversity of trilobites is pretty low? Are we seeing like a really low diversity of?
We're seeing, not like lots of members of the same groups. We're seeing, a few species representing the major different types of trilobites that were occurring at that time.
Complex life forms began with what is called the Cambrian explosion. The Cambrian explosion, once a mystery buried in stone, came into focus only recently through remarkable fossil sites like the ruined wash, Lower Cambrian Lagerstätte, seen here. The Cambrian explosion began roughly 541 million years ago, when all life was still confined to the oceans. In a blink of geologic time, just 20 to 25 million years, life underwent a radical transformation. Dozens of animal body plans emerged. Organisms developed hard parts, shells, spines, and exoskeletons for the very first time, making fossil preservation suddenly possible on a massive scale. This era marked the arrival of nearly all major animal groups, or phyla, that still exist today. The Cambrian explosion wasn't just an increase in life. It was the blueprint for complexity. It set in motion the biological drama that would unfold over the next 500 million years.
After collecting the Brandon Bridge fossils in the mid-80s, I moved to Colorado. This was the center of the cable industry, and I thought it was a good place to bring my film production company and distribution company. But when I got here, I realized that there was very little Paleozoic nearby, and I had pretty much given up hope of ever collecting another Lagerstätten. But when I was here, I met one of the grand old men of paleontology, Pete Palmer, and he showed me some amazing trilobites, and he said they were from the Lower Cambrian, and that this site held the possibility of being very rich in terms of at least trilobites and other fossils. And so he also said that the Denver Museum of Natural History had gone out there and exposed a bunch of the layers. And he told me what gave me directions how to get to the site. So when my collecting friend Jerry Gunderson came out for our summer trip out west collecting fossils, we decided we'll go to this site. And we did. It's out there by Area 51, amazingly. And when we got there, to our joy, we collected many, many trilobites.
Not just any trilobites, but the mother of all trilobites, the Olanellus.
A ruin wash site it's probably now one of the best Olanellid sites in the world because they're predominantly in North America, and there are less common ones in Siberia and in Morocco, but they're abundant in North America. They dominate these lower Cambrian beds, and this site is the richest available site now on the continent, and probably one of the richest that's ever been found.
Well, Olanelloid trilobites are considered to be really the most basal trilobite group, or among the first bona fide trilobites to appear and evolve in the fossil record. They're incredibly diverse at the time.
In fact, trilobites, after dinosaurs, are everybody's favorite fossil. Like modern crustaceans, insects, and spiders, trilobites were arthropods. Marine animals with hard exoskeletons and jointed legs. But what set them apart was the distinctive three-lobe design of their bodies. The very feature that gives them their name, trilobite. From head to tail, their bodies were divided into three parts: cephalon, thorax, and prodigium, each made up of segments that let some trilobites roll into a tight ball for protection. With complex compound eyes, some with hundreds of lenses, they could scan the sea in all directions. Others, blind and bottom-dwelling, relied on spines and pits to sense the world. They scuttled across the sea floor in shallow reefs and deep abysmal plains. Many had legs that also helped them walk, dig, and perhaps swim. For over 250 million years, trilobites thrived in Earth's oceans. Today, they are among the most recognizable and mesmerizing fossils from the deep past.
Oh, that's a lot of trilobites. That's really cool. Trilobites.
Burgess now is what they're saying.
Like all kids, our junior paleontologist helpers love trilobites.
And this one is like created of it. It has its little indent behind you.
Wow.
It's really cool. And look at this one over here.
These are trilobites, but they are very, they're lovely and they're very well preserved complete specimens, but the rocks have been squashed, and so they are deformed from their original shape. And we can see that because they're not bilaterally symmetrical, so they've been sheared. And you know, oh great, yeah, this one's got short and fat because it's been squashed in this direction. Yeah. And so it gets short and fat. And then we've got a long and thin. Do we have a long and thin? Oh yes, this one here.
Nigel, didn't you write a paper on?
I did, yeah. Yeah, so this one is long and thin, and this one is short and wide.
But I think in the case of the ruin wash, because it's a type of deposit that's referred to as the Lagerstätten, usually what that means is that lots of things get buried very quickly, and the types of conditions that are present really might kill those organisms, but also exclude the type of organisms that would come around later and sort of chew those trilobites and other things up and decay them. So I think in the case of the ruin wash, what we have are the actual carcasses themselves, not the molds, or at least not primarily the molds.
However, for the ruin wash Olanellus trilobites, the reign over the beginning of complex life in the early Cambrian seas ended almost as quickly as it began.
This bed is as rich as any horizon in terms of species abundance anywhere in the lower Cambrian, and yet the top of the bed, which is about 50 centimeters thick, is an extinction boundary, and there are no more Olanellids seen anywhere on Earth after that point. They disappear from the seas of the Earth, even though they dominated these seas for, maybe 10 million years prior to this event. And we don't quite know why what it is that the event was, but it's similar to several younger events that we've identified in the Cambrian that keep perturbing the normal evolutionary development of the trilobites.
Like collecting at the Brandon Bridge, one of the things I knew I should do is bring back slabs and let them wither, and which I did. And while I was sitting at home splitting some of the rock, a particular fossil appeared, and it blew my mind. It was a claw of Anomalocaris, and I immediately knew that this site was not only rich in trilobites, but had the potential to have soft-bodied animals.
Called by the famous paleontologist Stephen Jay Gould, a tale of humor, error, struggle, frustration, and more error. The Anomalocaris was once 3 different animals, until scientists realized the claws, body, and mouth all belonged to a single fearsome predator. The largest known animal of the Cambrian seas, it swam with undulating side flaps acting like a single efficient fin. Its tooth-ringed mouth was like no other animal, and its forward-facing spiked claws were perfectly designed for grasping prey. With eyes boasting over 24,000 lenses, more advanced than even trilobites, the Anomalocaris had extraordinary vision. This amazing predator remains a symbol of how strange and astonishing early life on Earth truly was.
So after that, the discovery of the Anomalocaris claw, I decided I would go out to the site at least once every year, probably in the spring before it got too hot, which I did. And I began finding other soft-bodied animals, plus a plethora of trilobites, complete.
During the 1990s, word began to spread throughout the paleontological community that the United States had its own Cambrian Lagerstätte, which included some of the earliest soft-bodied animals ever preserved.
In the winter of 1999, I was told by Pete Palmer that there was going to be a great gathering of institutions and fossil collectors from those institutions, and they were going to come out to Ruin Wash in the spring, and I was invited to come out there and be with them, which I was eagerly and quite happy to do.
The expedition out to the Ruin Wash locality was really an excellent opportunity for scientists at a variety of different career stages to get together, to collect fossils, also sort of to discuss the paleontological significance of this site.
During their visit to gather up the fossils from Ron's 4 Lagerstätten, including Ruin Wash, Ron invited Dr. Hughes, who was at the collecting expedition, and Dr. Honda, who later visited Ruin Wash, to view the archival footage of the dig for the first time.
Oh, so I should go over here?
Yeah.
Yeah.
Of course.
Put Ron in the corner.
Put Ron in the corner.
All right, well, we're going to take a little look here at the video that was made in 1999 of our excavation at Ruin Wash. So we'll just zip through a few frames of this and just comment on some things. But basically what happened was that, we approached, various institutions approached the BLM to get permission to excavate at Ruin Wash. And so there were paleontologists coming from Yale, from Harvard, from University of Kansas, from UC Riverside, Mark Webster and myself. So I didn't really realize this until this video was being made, that it's named after the ruins at Ruin Wash. So that's not perhaps so surprising, but here is the ruin that's a little bit off the track there. So these are the Gunters, yeah. So Glade is the younger man there, and you can see that they know what they're doing.
Generations of Gunters, they're working away.
Yeah, as Ron says.
Slave labor.
They're doing it, and they're knowing how to do it, and they're collecting. Yes. So they're some of the best specimens that are being collected. But it's very, very interesting.
Fred Collier.
Yeah, there's Fred Collier. So, whoops, I was just going to stop that on Fred. So, Fred was the collections manager at the time at Harvard. But he'd been in the Smithsonian for many, many years. Most of his career was collections manager in the Smithsonian. And he was very great at interacting with amateurs, and he was also very kind to graduate students and accommodated me when I was working in the Smithsonian at the beginning of my PhD. And Fred and Martha were just wonderful people and super kind. So it's lovely to see this film that I've never seen before, actually, and see some of our friends that are no longer with us. So that's Fred. And so we had along the strike in this area, the BLM came and we brought a front loader in and they excavated so that these rocks, which were originally horizontal, were tilted. And so we could find the particular layer and then work along what's called working along strike to expose areas where we could see these fossils. And oh, yeah, there's two handsome gentlemen.
Here a young Dr. Nigel Hughes talks about this extraordinary Lagerstätte.
You've got a lot of complete specimens, so that tends to mean that because these animals fell apart very quickly or after they molted or after they died, if you get complete ones, it means that they've got to be buried very quickly. Because if you're going to get complete things preserved, you've got to have them suddenly or fairly rapidly swamped by sediment and buried so that they don't get disturbed by currents on the seafloor. So we've got to get these animals, we've got to get them living there, and then we've got to quickly bury them in some way so that they get preserved complete. Otherwise, they're going to fall apart very rapidly as their soft tissues decay after the animal is molted or after the animal, if it's a dead individual, after the animal has died.
Yeah, what I love about this kind of thing, other than the fact that so many institutions are participating, which is fantastic, is that it is a collaboration between amateur and professional paleontologists.
Yeah, absolutely.
And that often is a source of, it's a sore spot for a lot of paleontologists, that we do have an amateur collecting group or community, but oftentimes it's those community people that are the ones that are actually going out and getting the fossils for us to study.
I would not be talking to you now, and you wouldn't have had me as an advisor if it wasn't for Ron and Jerry. So, I would have found probably 3 trilobites in the whole of my PhD if I'd been left to look. So here's what's. Here's Bruce.
Dr. Bruce Lieberman would go on to become the expert of the soft-bodied animals found at the ruined wash Lagerstätte.
The ones that we've seen so far are enigmatic in the sense that we're not exactly sure where they fit in evolutionarily. They're probably related to the great group, the arthropod group in some sense, so the group that would include the modern insects, spiders, and crabs. So somewhere within there, but we're not exactly sure where they fit in.
Just a fantastic place to work at very pleasant temperatures that time of year, no insects, and the wind wasn't too bad, so we really had a great time.
At the gathering out there at Ruin Wash in 1999, I met Dr. Bruce Lieberman. And it turns out that he was going to be the person to describe a number of the soft-bodied animals that were being collected. And so I decided I will send a representative selection of the fossils I have to him, which I did do. But I kept quite a large collection from at home in Boulder, Colorado.
There's also a range of other things that we know, partly by discoveries at the Ruin Wash, but also from discoveries from other soft-bodied deposits, Lagerstättens, from around the same time as Ruin Wash. So there would also have been things like jellyfish, different types of worms, And indeed, some of the things that we can say were present at the time were first discovered, or some of the first places they were discovered were at Ruin Wash.
Beautiful selection of specimens from Ruin Wash. Here we've got, the complete Nephrolanalis, so the trilobites.
In addition to the hundreds and hundreds of Olanellus trilobites, many soft-bodied fossils that Ron collected were also on their way to the Cincinnati Museum Center.
Of the complete trilobite. So that's one of the reasons why this locality is so important. Here's another slab with trilobites on, not just Nephrolanalis, then some of the other Olanellus trilobites. And you can see how many of them there are together. But here, alongside, you can see a structure that is not part of the trilobite. It is this kind of serrated lance-like structure, and that's giving us the indication that not only are the hard parts preserved, but this is in one of those localities in which soft tissues or semi-rigid tissues are being preserved. And we see examples of that kind of preservation, which makes this one of these soft-bodied sites.
So one of the distinctive elements of collecting out there in Ruin Wash was that you had to wait for the rock to weather, and if when it was weathered, you could walk along this long ridge of tilted rock where you could just move along, and people have been collecting and extending the layer, and eventually identified that there was a pretty narrow band where all the soft-bodied animals were coming from. Sometimes along that long band of collecting material, they'd be red in color, which was a definite sign for me to start splitting that rock. And as a result, I got a lot of the soft-bodied animals that are brilliantly preserved with a red tinge.
Now, to focus on the preservation, one of the distinctive things that we do see in the preservation of fossils from Ruin Wash is that they often have this real red tinge or hue that helps to identify, or it makes it easier to pick these out in the field. And what we're pretty sure these is they're definitely high in iron, which kind of gives them that reddish color, well, something akin to what we would today refer to as rust. Probably when the animals were first living in the environment, though, there wasn't rust or anything like that was present, but iron is always present in the oceans. And one of the things that we connect to soft-bodied deposits, the way they are preserved, or one of the ways that they're preserved, are under conditions that are low in oxygen. When there's low oxygen condition, it prevents scavengers and other types of things like bacteria that would break down or decay organisms from being present. And such environments tend to be rich in pyrite. Then hundreds of millions of years later, when these fossils come to the surface or near the surface, either groundwater that's high in oxygen or is flowing through them, exposing the pyrite to oxygen, or when they're actually exposed on the surface to air, that oxygen is breaking those down. So you have sort of a conversion of the pyrite into something that ultimately imparts it this reddish hue.
And then who are these guys right
Yeah,
here?
so coming into that, so here is the shell then, or weakly biomineralized shell of a Tuzoia.
The Tuzoia was a large shrimp-like creature growing up to about 9 inches long. It had a bivalve style shells, like a clam, protecting its internal parts. Their shells were covered in a net-like pattern and had spikes along its edges. In addition, the Tuzoia had big stalked eyes, long antennae, and multiple pairs of spiny legs, some designed for grabbing or walking, others for swimming. Tuzoias probably stayed close to the sea floor.
So here are these sort of conical, narrow triangular animals. These were curious animals that had a biomineralized shell, but are preserved in this
assemblage?
Well, hyolithids are one of these organisms that for a long time were thought to be difficult to assign to any particular modern group. But I think consensus is building now that this is a group that may be closely related to the mollusks. So the group that includes among modern organisms, snails, clams, the nautiloid, squids. So hyolithids could comprise an important early record of mollusks from Ruin Wash.
That goes in the problematic section of the collection,
Yeah.
where we put all the things we don't know.
Looks like a
what they are.
blob. Yeah.
But the structure.
Yeah. Yeah, structured blob. I'm not gonna.
This might be a Canadespis, a small two-shelled arthropod that crawled along the Cambrian seafloor, using its legs to stir up mud in search of food. Fossil Canadespis from Ruin Wash show it was among the first animals with shells and jointed legs.
And just a load of organic material and maybe algae that's preserved on the seafloor.
So many bizarre creatures waiting to be studied and described. But here's the story of one that was described.
Perhaps the most exciting experience I had in terms of animals I collected there, or fossils I collected, was there was something that was living in kind of a colonial type situation, and it was the strangest looking animal. And I sent them to Bruce Lieberman in Kansas, and he didn't know what they were either. I thought they were some early form of us, but nobody could say for sure. And then perhaps 20, 22 years later, Bruce calls up one day and says, guess what? We know what those fossils are. And it turned out to be this thing called a herpagaster.
This was a fossil that was discovered by Ron Meyer and ultimately shared with me and my colleague Julian Kimmig, and we described it as a form called herpagaster. It's kind of a weird stubby thing with a gut. It's partly coiled. They had these tentacles. Probably was a filter feeder. So that's one of the distinctive things that are known from Ruin Wash, that have these soft tissue preservation.
Interesting, the herpagaster animal has been proposed as a part of an early branch of animals related to the common ancestor of echinoderms, like starfish and chordates, like us. It's fun to imagine starfish as our closest animal relatives.
Eventually, commercial fossil collectors learned about Ruin Wash and the many trilobites that could be found. And so they went out there and started collecting them and selling them. And it became sort of like a three-ring circus. And eventually the BLM said, that's it. And they went out there and covered up the whole formation. And now it's inaccessible to anybody. You wouldn't even know it was there.
The Ruin Wash Lagerstätte now stands as one of the most pivotal fossil sites of the early Cambrian period. Here was found not only the ancestral origin of trilobites, but also a rich array of soft-bodied creatures, many still awaiting formal description.
In the next chapter, many of the fossils and animals of the Brandon Bridge Lagerstätte returned, only bigger. While we were collecting at Ruin Wash, Jerry told me he had seen fossils like the Brandon Bridge animals during a fossil club meeting. They came from a quarry near Clinton, Iowa. I stopped there on my way to Wisconsin and quickly found a specimen like this phylocarid. That summer, we collected many more fossils from what became known as the Scotch Grove Lagerstätte.
Tucked away in the Silurian rocks of eastern Iowa lies a site that quietly rivals the great fossil beds of North America, the Scotch Grove Lagerstätte. Unassuming and long overlooked, yielded the largest collection of soft-bodied Silurian animals in Ron's personal collection.
Certainly there were clear comparisons with Waukesha. I mean, the two faunas are not that different in age. So Scotch Grove is slightly younger than Waukesha. Presuming one had a good handle on the environment at Scotch Grove, all these things give us an insight into, different seabed settings, different ecologies at that time, and what kind of organisms were cohabiting. And if you're confident that they're actually living together as well as getting fossilized together, you've got a great story. That's what exceptional preservations are all about.
Despite producing hundreds of exquisitely preserved soft-bodied specimens, including arthropods with delicate muscle impressions, floating fossilized egg cases,
From Scotch Grove.
From Scotch Grove.
and worms frozen mid-motion in stone, this site remains virtually unknown. Only 2 formal scientific papers have ever emerged from the Scotch Grove Lagerstätte. No general introduction, no global headlines. One of those papers was written by Dr. Nigel Hughes, who arrived at Ron's house the night before the next day's arrival of the Cincinnati Museum Center's curator, Dr. Brenda Hunda, and her crew.
Brigg was here, I think, around 2004, something like that, going through this, and he gets kind of obsessed, and he was making little notes, and not this one, let me see. Yeah, so here, this is a typical specimen, and he was looking at this, and his note was problematica. Like, what in the heck is that?
Well, I can see why he said problematic, but it's a typical piece of Scotch Grove. But look at these impressions. Then I have no idea what they are, but I'm going to have a little look with my my hand lens here, and I can't tell you anything further. But it's the same material that we got that beautiful conularia out of.
So just to bring the story, let's pretend this is the conularia.
Yeah.
And he sees it, and he says, "Oh my God, this is a conularia, and there are soft parts." I said, "Well, yeah." And he said, "I have just the person who we should give this to."
Right.
And it was you.
We were the lucky recipients, yeah. I became a conularia expert because there's hardly anybody who studies them. And then, it was great when Derek recognized those specimens.
The conularid animal was encased in a rigid cone with 4 folded sides, and it looked like no animal alive today. For decades, its identity was a mystery. Was it a mollusk? A worm? Something entirely alien to biology? After 30 years of studying a single specimen from the Scotch Grove Lagerstätte, Dr. Hughes resolved the mystery.
So the jellyfish?
So that they are related, to that large group, the cnidarians, and there are some particular group of cnidarians, Storomedusans, and the conulariids are the polyp phase, so that's what sits on the bottom, and may have pumped out a load of medusa, so little jellyfish, or may have directly had sperm and eggs come out. There is a midline, and then there are these funny little ridges that intersect at the midline.
It's so beautiful, though.
It is beautiful, and it has this kind of brown color to it, and even in this one, although the fossil is gray, there's a little tint of the brown coloration here, and that's because this is biomineralized. This is made of the mineral apatite, so calcium phosphate. So normally in a conulariid, if we're lucky, it's preserved, but what is preserved is the biomineralized part, the apatite. But in the one from the Scotch Grove, the preservation was really super unusual. Not only was it unusual because the soft tissues were replicated in silica, so like glass, but not in apatite. In fact, in some of those specimens, the apatite had dissolved. But the other thing that was really weird about, we'll take this one here, is that, this is a view of the side of the conulariid. In the Scotch Grove one, it was a view as if you were looking down from the top, and it was looking into the apex, and you could see the soft tissues that would have been inside a four-sided pyramidal structure. This one's been squashed, so it would have had four equal sides, but of course in the rock record it gets compressed and turns into this kind of flattened structure. But in Scotch Grove, this thing was living on the seafloor in its original position, and the soft tissues inside the cavity were preserved.
Perhaps the most exciting specimens Ron and Jerry found in the Scotch Grove Lagerstätte were these horseshoe crabs. Known as one of the oldest living fossils, horseshoe crabs are ancient marine arthropods. Arthropods that were already complex animals, well adapted to life in Earth's early near-shore ecosystems. To Ron and Jerry, they looked remarkably like the horseshoe crabs they found in the Brandon Bridge Lagerstätte. In 2005, Dr. Derek Briggs and his student Rachel Moore described these horseshoe crabs as a new species, and they named it Venustulus wakashanensis. It had 10 segments behind the head, with the last 3 forming a narrow tail region. The preservation is so fine that even ridges, spines, and leg segments are visible. It predated other known horseshoe crabs, extending the known evolutionary timeline of these creatures back in history. So it was natural that Dr. Briggs and Rachel Moore would describe the horseshoe crabs from the slightly younger Scotch Grove Lagerstätte. They named it Commentaria grovenensis in a 2011 paper.
My particular interest in Scotch Grove was obviously the horseshoe crabs with my student Rachel. What was exciting about that material and the handful of specimens we got hold of was that the musculature was preserved, and the musculature in the Scotch Grove things is a lot simpler as far as we could figure out. So they had rather different muscles manipulating the hinge line between the head structure and the rest of the animal, which I guess was somewhat interesting. And they also had strange muscles that connect the tergites, the segments, if you like, of the posterior part of the animal, which I think we thought may have been useful for controlling the volume of that part of the animal, and possibly also in terms of how these things probably enrolled in a loose sense to protect themselves from predators. I suppose folded as opposed to enrolled, really, strictly speaking. So they had rather different muscles to the Mesozoic ones, which would imply that they were down, in the stem, an early branch off. And it's unusual to have soft tissue evidence that that's the case, as opposed to relying on just the hard parts. So I guess that was the excitement for us.
There is one more amazing finding that came from comparing the two Silurian Lagerstätten.
We found an example in Scotch Grove that we actually assigned to the same species as the Waukesha, one of the Waukesha, the Waukesha sin Deciphering. So the thing called Venustulus, we named it Venustulus waukeshaensis, very imaginative. And that turns out to be not just at Waukesha, but also we had a specimen that turned up at Scotch Grove. So it would suggest that there are, strong parallels in the whole fauna, but even down to individuals, which I think is quite exciting.
One of the moments I'll never forget was seeing Dr. Hunda's reaction when she first laid eyes on some of the Scotch Grove soft-bodied fossils. That would soon become part of her museum's collection. I could see the excitement. It reminded me just how special these Lagerstätten really are.
Wow, what is that?
I have no idea. So this is the Silurian Scotch Grove from Iowa. And it's another one of these fantastic fine-grained sediments that has preserved the soft tissues of the organisms that are occurring in this setting. And there are a whole wide range of things here. And the only thing that we can really say that distinguishes one from the other is that some of them have this seriated or segmented structure running down the body. And it's really clear in this one here. See that really beautifully. And these ones here, and these two are kind of similar in the lots of segments, but this is much wider than that one. So many organisms can show serial arrangement. We think of arthropods, you know, those animals with the skeleton on the outside and that go through molting. But there are a lot of worms, annelid worms, that have that kind of segmentation. And even vertebrates, you know. We have segmentation in our backbones, for example. So it's certainly a segmented organism, as are many of the other fossils that are found here. See, these beautiful tiny segments.
Oh yeah! Wow.
Down the trunk of the animal.
Wow. Yeah, look at.
Yep, seen them there.
Yeah.
And these things, I mean.
Oh my gosh.
These things that, you know, maybe worms of some kind, but they've got those little setae that are sticking out.
Yeah, that's pretty amazing.
And, you know, you really want to look at these in detail to see whether there are any structures that you can discern that really tell us a little bit more.
So.
And then here we've got all these things that are not so much segmented or arranged in different ways. We've got these wonderful, where are those? So these look like dendroid graptolites. So you can see these
I was gonna
sort
say,
of fan-shaped
they do.
branching structures here. And then we've got this worm that's beautifully coiled up.
Doing his worm-like behavior.
And things with two shells, in a kind of bivalve shell, but not necessarily a mollusk, because some arthropods have a bivalve shell too. So
They do, yeah.
what you see in there, Brent?
I see lots of notes. Here's another example of one of these guys here, but less obvious. I think you would tell me that most of these things have not been described before?
No. And we see a note there from the great Derek Briggs saying, what does it say?
Egg string?
Egg string. Egg string. So he thinks that this may be a little pouch of eggs that's attached by a little filament to
Eggs of what?
Eggs of probably some arthropod, right?
Yeah, no, but that's cool.
Custard and
then there's one more to look at.
Yeah, I'm going to put this one right here.
less interesting problematic.
Speaking from somebody who's made his entire career out of problematica.
Yeah.
For me, it's all interesting.
See, I'm an interesting
because I have no idea what any of it is. Awesome.
Paleoscalicid. Okay, oh, look at these little worms here. And Derek has noted them as belonging to this because I think he sees regular tubercles, but he's a better man than I am because I can't see a tubercle for, maybe something there.
Have they ever found like any of those like phoronid worms and stuff like that?
Yeah.
In any of this kind of stuff? You know, the kind of things that you see in the Burgess? And
yeah, I'm not sure. Well,
that kind of
Ruin wash.
Ruin wash
have
down
found
there.
them?
But up in the Silurian, I'm
Up in the Silurian, yeah.
not so
so much.
sure.
Yeah.
And Derek says coprolites here on this. So that's fossilized poop. Always fun to see, but I'm not sure which.
Look at, what are these?
F.
This is the amazing thing about looking back in time in the fossil record and realizing that there are things in there that you can't even figure out what phylum they belong to. That's a pretty fascinating place to be.
There were many more Scotch Grove Lagerstätten soft-bodied animals tucked away in beer flats, including the largest specimens.
You're not special certified.
All right, you know what I'm going to do? I'm going to put these, make sure it's the same locality. Yes. Ooh.
Ooh. There's an ooh in there.
And then we're going to put these down here.
Do I get to see the ooh?
Just.
Ooh. Oh yeah. I think this one needs to.
Oh yeah, needs to take a little.
It needs to be elevated to the top. Yeah.
But what about trilobites in the Scotch Grove Lagerstätte? Unlike the Brandon Bridge's large variety of trilobites, only a single small dominated trilobite fossil was found by Ron and Jerry in the Scotch Grove Lagerstätte. The second Lagerstätte, discovered by Ron and Jerry, was in one of the most unlikely places, the Upper Peninsula of Michigan. This rugged stretch of land, wedged between Lake Superior and Lake Michigan, is best known for its historic copper mines. Heavily forested and sparsely populated, it has never been considered a fossil hotspot. Yet the few fossils that have been found here date back to the Ordovician period. Nearly 500 million years ago, Earth entered another time of remarkable transformation. The Ordovician period, stretching from about 485 to 443 million years ago. The Ordovician was a time when life surged across the seas in an explosion of biodiversity. Warm, shallow oceans flooded all the continents, forming vast inland seas teeming with life. Here, trilobites crawled along silty sea floors. Giant nautiloids hunted with precision, and the earliest coral reefs began to take shape. Brachiopods, bryozoans, and the fearsome euryptids, sometimes called sea scorpions, shared this ancient world. Back then, North America looked nothing like it does now. Vast, shallow seas stretched across the continent, represented here in light blue, giving way to deeper oceans beyond. Only a few land masses broke the surface, the largest of them near what is now the Big Hill Formation. In the early 21st century, there were no Ordovician Lagerstätten in North America. That changed in 2013.
In 2013, my fossil collecting buddy Jerry Gunderson and myself was shown a fossil at a fossil show that to us was a euryptid. And we asked him where he found it, and he wouldn't tell us exactly, but he said it was north of Green Bay, Wisconsin, and it was in the Ordovician. And so we figured that's probably the Stonington Peninsula in the Upper Peninsula of Michigan. And so we drove around quite a bit there, and we got into the middle of the peninsula, which is a very isolated type environment. Hardly anybody lives there. We found this giant quarry. And then we thought, well, let's take a look at that. And so we went into the quarry, drove in. People were working on that time. And we were moving along the edges, and I reached in over the ledge and pulled out a rock, and there was oh my God, we thought, here's a euryptid just like the one the collector had showed us. And so we thought, this is really cool. It'd be neat to be able to collect here. Well, it didn't take long for the people operating the quarry came over and said, you got to leave. You don't have permission to be here. So we had to leave. And then the next thing we had to do is figure out how we could get in there to collect fossils.
Ron and Jerry needed permission from the Delta County Commissioners to collect fossils at the quarry. They submitted a letter outlining the site's potential as a significant scientific discovery. Permission was granted by the commissioners with 3 stipulations. They had to provide liability insurance, notify Highway Superintendent Jody Norman at least 1 week before each visit, and ensure the fossils would be placed in the scientific repository. With those conditions met, Ron and Jerry collected at the quarry every fall and spring until the pandemic halted their work.
When we came back for the first time with our newly granted permission to collect in the quarry, we noticed there was another quarry on the other side of the street. It was part of the Forest Service. It was owned by the Forest Service, and it was not in operation anymore. So we went over there, and we found the same strata, but in a very isolated way. We found a few gnawed-whites. But in the main quarry, what had happened is that a commercial operation began, and they were making flagstone to put on the sides of buildings decoratively. But what was unfortunate for them is that the stuff weathered quite easily, and so they had a lot of complaints, and it was not a viable business anymore. So they decided to sell the quarry to Delta County, and the Delta County people used it for crushed rock for their roads.
Collecting in the quarry was very challenging. Ron and Jerry either had to collect along the edge of the quarry where weathering had taken place, or, remarkably, on the floor of the quarry in the areas the crews had scraped clean in advance of the next quarrying operation. Here, the trick was to find what they called pops, structures that needed to be loosened and lifted with their collecting tools. Almost immediately, they found what they believed were jellyfish. Jellyfish that probably died and washed up on a beach, like these seen here from a Florida shore. And with that, they knew that they had stumbled onto a discovery of exceptional fossil preservation. Jellyfish, also called sea jellies or simply jellies, are some of the most ancient and otherworldly animals on Earth. What is called a jellyfish is actually the Medusa phase of certain gelatinous creatures belonging to the subphylum Medusazoa, a major group within the larger phylum Sideria. Their most iconic feature is the bell, a soft umbrella-shaped structure made mostly of a jelly-like substance called mesoglia. This mesoglia acts like a hydrostatic skeleton and is made up of more than 95% water. It gives jellyfish their graceful, ghost-like form. Most jellyfish drift freely through the oceans, though a few spend their lives anchored to the seafloor. Their bells contract in rhythmic pulses, pushing them gently through the water. From the underside of the bell trail long, often delicate tentacles armed with stinging cells, used to catch prey or fend off predators. Jellyfish grow quickly, often maturing in just a few months, then dying soon after reproducing. These creatures are not just survivors, they're time travelers. Fossil evidence suggests jellyfish have been swimming in Earth's oceans for at least 500 million years, and perhaps over 700 million. That makes them the oldest known animals with multiple organs, predating the dinosaurs by hundreds of millions of years.
They're all jellyfish, are they? Well, let's have a look.
Full of jellyfish.
And they look like, I guess they look like a jellyfish would look on the shore, you know, kind of washed up. So this, of course, is the soft parts of the jellyfish preserved. Ooh. You can kind of see it. You know how when jellyfish get all shriveled up on the shore?
Yeah.
Well, you can kind of see that. If you put that, you have to put your eye real close.
Okay.
And hold the fossil real close too. Yeah. So even closer. Yeah. That? Oh yeah. So you can see. Yeah. Should we show your mum?
Well, maybe.
She doesn't care about jellyfish.
Yeah. She's just got to stuff them in a drawer somewhere.
Oh my goodness. That's awful. Oh wow. It has like the little central structures and everything.
So there are only, less than 6 sites that preserve jellyfish.
Yeah. You guys, that's really cool. Because when you think about a jellyfish, it's basically a bag of jelly.
Yeah.
And the fact that it has become a fossil is a really amazing thing.
Yeah.
And how old are these now?
The Ordovician.
So these are 475. Are they middle Ordovician?
Yeah, they're upper Ordovician.
Okay, so
to this. Yeah.
these are almost 500 million.
Close to the
years old.
extinction.
1 billion years old. Jeez. Yeah, that's like crazy amazing.
Never been described.
Wow. Wow.
So one of the conditions of our collecting is that the significant fossils would end up in they would end up in museums and be made available for scientific research. And we had a good working relationship, Jerry and I, with the University of Wisconsin Geology Museum. And I would say 90% of the fossils went there. After each time we collected, we would sort out and label and send a huge collection to Wisconsin. I would take a few fossils from my own private collection, which I brought back to Boulder. And when we had enough, I contacted Dr. Briggs and said, I think we got another Lagerstätten here. And what should we do with them? And he had been working at the time with a postdoc student, Dr. James Lambsdale, and he was something of an expert on Euryptids, so it seemed natural that he would become the lead paleontologist to study these animals.
So I guess at that stage, James Lambsdale, who's ended up now as a professor at West Virginia, was here at Yale with me as a postdoc. So James and I helped you to do an announcement paper, if you like, about the range of taxa there.
One other thing we found that was quite of interest to science was that there was ancient algae, at least 2 different kinds, that not very common, but the preservation was remarkable.
They don't preserve well because of their very nature. They don't have any kind of shelly material in them. And I think Big Hill is close enough to land, if indeed these things are terrestrial, or at least they're living in shallow water. So in that sense, they're getting preserved here where they don't necessarily get preserved in other places.
Most of the fossil algae collected at the Big Hill site bear a striking resemblance to today's marine red and green algae. Ancient lineages that still thrive in warm, shallow coastal waters around the world. These living counterparts, especially abundant in tropical and subtropical seas, echo a biological design that has endured for over 1 billion years. Algae were among the earliest architects of complex life, laying the foundation for modern marine ecosystems. The Big Hill fossil algae offer a vivid window into this evolutionary legacy, tracing the story of life back to when algae ruled the seas and set the stage for all that followed as animals moved onto land. In terms of animals moving from the ocean to the land, arachnids, the group of arthropods most often feared and misunderstood by humans. They include spiders, scorpions, ticks, and mites. Adult arachnids have 8 legs attached to a central body segment called the cephalothorax. In some arachnids, the front pair of legs has evolved into sensitive feelers. In others, different limbs have enlarged, giving the illusion of extra legs or tools for grasping, sensing, or defense. Today, nearly all arachnids are land dwellers. There are over 110,000 known species, and likely many more yet to be discovered. But here's the twist. One of the most intriguing ideas in evolutionary science is that arachnids were the very first animals to crawl out of the sea and onto land. If true, the moment marked one of the greatest transformations in the history of life on Earth. So, what were their oceanic ancestors? Where did they live? And what did they look like? That's where the fossils of the Big Hill Lagerstätte came in with the discovery of some extremely rare arthropods. The most common large one being a creature Ron and Jerry called chazes.
What do you got?
It looks like a nautiloid and a chaz. It's related to the Euryptid.
Wow. That's fantastic, huh?
Yes. This is a new genus, new species at least.
And what's the name? This is one of the main things we've been collecting. And these are the only complete ones ever found, ever.
Yes.
So Nigel, where do they sit in terms of the arthropod family tree?
The Chasmataspids.
Yes.
I think that they're chelicerates, so they're
Yeah.
On the spider scorpion side of the arthropod world, look, you can see the frontal appendages in this.
Oh yeah, right there.
This, when it's cleaned up, you'll just be able to.
Look, future paleontologist.
Yeah, look at this. So, you often see the main part of the fossil, but you don't see the limbs that are preserved. But here you can see these limbs at the front and with pincers and all sorts of things, like a Swiss Army knife with an appendage for everything.
This fascinating creature belongs to an ancient group of marine arthropods belonging to a subphylum of Chelicerata that may have given rise to the first animals ever to crawl onto land. These early predators thrived in prehistoric seas and are ancestors to some of today's most resilient survivors. Among them are the Xiphosaura, better known as horseshoe crabs, the formidable Euryptids, or sea scorpions, and the mysterious extinct group called Chasmataspids. Together, they paint a vivid picture of life in Earth's early oceans and hint at one of the greatest evolutionary transitions in history.
The most common arthropods that we find at Big Hill are these strange chelicerates called Chasmataspids. They are very, very similar to Euryptids, and in fact, when we started studying the material, we assumed it had to be a species of Euryptid purely because of the size, because these things are quite large. They can get up to 10 or 15 centimeters long. When we looked at them, though, we were able to see that underneath some of the body segments, there's this fused shield that actually forms what we call a buckler right behind the head. And it consists of 3 segments. And this buckler is only known in Chasmataspids. So we found out that the most common arthropod at this area was from an incredibly rare group from which very little is known, where the majority of species are less than 2 centimeters in size. So this thing was unique and really gave us an exceptional insight into this group.
One of the reasons the Chasmataspids fossils from the Big Hill Lagerstätte are so often found in clusters is because they're not actually full bodies, but molts. These shed exoskeletons drifted together in the calm near-shore waters, eventually settling side by side on the sea floor.
The other really interesting thing is that because these are molts, and we know that they are molts because The plates at the front of the head are split apart, and the buckler itself is actually split open where the animals crawled out. We can, first of all, get a sense of the three-dimensional shape of these animals. We can almost dissect through them to see how they were constructed from the top down through to the underside. But it also shows that these things were living very, very similar to Eurypterids. They were coming into this area to shed their exoskeletons in a big group. This is probably something that they were doing in order for some degree of defense, because when an arthropod sheds its skin, it's very, very soft for a few hours once it comes out. And so this is something that we know Eurypterids also did, and this is something that shedding their exoskeleton is common to all arthropods. Trilobites do it, modern spiders and scorpions do it, insects do it. And the interesting thing about this is obviously that an animal is going to leave multiple shed skins over the course of its life. It will only ever die once.
The biggest, oh wow, moment for Jerry and Ron came when they found this Euryptid specimen. A specimen with some of its cuticles preserved. Euryptids turned out to be the second most common fossil in the Chelicerata family group found in the Big Hill Lagerstätte. Euryptids, often nicknamed sea scorpions, first emerged around 467 million years ago during the Ordovician period. They flourished throughout the Paleozoic seas, where they became dominant predators and a vital part of ancient marine ecosystems. Despite their nickname, sea scorpions, most Euryptids weren't marine in the strictest sense. While the earliest species lived in salt water, many later forms evolved to thrive in brackish estuaries and even freshwater habitats. They were not true scorpions, though they shared a similar body shape and predatory behavior. Interestingly, the Big Hill Lagerstätte contains at least 2 new species of Euryptids.
Specimens from Big Hill are very, very interesting because they seem to indicate that they might be some of the earliest representatives of a couple of groups that we otherwise only find from the Silurian onwards. So they'll be the oldest representatives of a group called carcinosomatids, which are generally big predators with very, very large spiny appendages at the front, and also a group called dodecopterids, which are particularly unusual. They have strange legs and paddles that it's been suggested that they could potentially almost hover in place when they're swimming. The other really interesting thing about the Euryptid specimens from Big Hill is the way they preserve their cuticle, their skin, in extremely fine detail. We actually can find it flaking up off of the fossils themselves. And so it's really interesting to look at the fine detailed structure. And in fact, we have used scanning electron microscopy to look at some of these fragments of Euryptid skin and try to look at the different layers that you find within that cuticle.
Euryptids weren't the only predators represented in the Big Hill Lagerstätte. Nautiloids, known as one of the earliest cephalopod animals, their carcasses were found in abundance as well.
Yeah. So this is a bunch of, this is something totally different. So these are mollusks, so they're related to snails and clams, but these things are much more squid-like. So you can think of the body of a squid, and inside there's a skeleton, and you can see the internal divisions here, and then this material going down the central axis. These were, animals that certainly swam around. They weren't hanging out with legs on the bottom. They were swimming around, and they were fearsome predators at that time. So yes. Whoever was scuttling around on the bottom needed to watch out for these guys.
Usually a trilobite.
Yeah.
However, the most convincing evidence that the Big Hill Lagerstätte represents a near-shore paleo environment was the discovery of what is known as the world's oldest living fossil, the horseshoe crab.
When I first saw pictures of this animal, I really thought it had to be some weird echinoderm or something like that. It didn't look like any other horseshoe crab I'd ever seen. So we knew that this species, which certainly had to be a new species, was extraordinary. But we didn't really know how extraordinary until we got it underneath the microscope.
What Dr. Lambsdale saw on this Big Hill fossil horseshoe crab might rewrite evolutionary history.
It has this interesting stain around the front of the head shield, which it turns out is in the same position and general shape as the ovaries in modern horseshoe crabs. And so when we looked at this material underneath the microscope, we found that within the ovaries are little spherical eggs. And so that we know that this was an adult female, which is very interesting because it is much, much smaller than modern horseshoe crabs. And it preserves some of the oldest known arthropod ovaries. And gives us a sort of amazing insight into some of the earliest horseshoe crabs' reproduction. It's something that, you know, every scientist dreams of getting access to material like this.
Unlike many other fossils at Big Hill, this horseshoe crab wasn't a shed mote, it was a living animal. And today, we know the horseshoe crab crawls out of the water to lay their eggs on land. That behavior offers a powerful clue. It suggests that the Big Hill Lagerstätte captures one of the first steps in the great journey of life onto land, a journey that would one day lead to us.
Big Hill's actually very interesting in its age, being relatively old and preserving all these different arthropod groups in this environment because arachnids are one of these arthropod groups that make it onto land. And so we're looking at early ancestors or offshoots of this lineage. And we can see that even so early on in the evolutionary history, chelicerates had an interesting relationship with these marginal environments, either going into them to shed their skins or moving into them to breed. And for eurypterids, at least, we think that they were able to move onto land for periods of time. They had respiratory structures that allowed them to breathe both in the water and in the air, and that later species move into freshwater rivers and lakes and were using their ability to breathe air to move between lakes for breeding and feeding. And so this is a really interesting snapshot into the early evolution of this very successful terrestrial group.
So here's some small ones that we can wrap up. Okay.
Small white paper.
Yep, that one's good. And just wrap it in there like...
We were talking earlier about how this is like Christmas for paleontologists, except that we're wrapping our presents and we already know what's inside them.
For Jerry and Ron, the fossils from the four Lagerstätten didn't just tell the story of early life. They allowed them to participate in the journey of discovery. A journey of discovery collaborating with an amazing lineage of paleontologists, each standing on the shoulders of those before them, building a living scaffold of knowledge that began with Dr. Derek Briggs.
You get this kind of spider's web where, you know, I don't know how many, 30 plus, nearly 30 or 40 graduate students, and a number of those have been very successful and have gone on to spawn, wrong word, a coterie of graduate students and so on. So it potentially expands. But the more exciting thing is that, you know, many of them have done really quite interesting science and in many cases relied on folks like you, Ron, because, you know, with the best will in the world, we don't spend enough time in the field and can only cover a fraction of the kinds of things that are out there. So we're really reliant on, you know, people like yourself and Jerry.
Derek had a whole string of students, but I was his third, and was working in the upper Mississippi Valley too. Derek has had a whole host of students who've worked on Silurian sites and things, and then his students have had students. So there's this lineage of people.
When they found the conodont material from Granton, the three of them, Derek Briggs, Ewan Clarkson, Dick Aldridge, got a grant from the UK equivalent of the National Science Foundation to look at these things, and there was money in that grant to employ a researcher, and that researcher was me. So it was my first research job after my PhD, so I think I was probably Derek's first postdoctoral researcher, actually.
In academia and in science, there's kind of a lineage that we pass our information along. And it's I like to think of it as a academic family. So Nigel is my academic father, and Derek Briggs is my academic great-grandfather, and Mark Webster is my academic brother, and that's truly how I see these people.
So obviously, I myself, very early on in my career, got to work with Derek Briggs, who is perhaps most famous for doing work on Burgess Shale and other exceptionally preserved faunas. And so it was great for Derek to sort of put me on to working on the Big Hill, and we've collaborated for many years since on both the Euryphids that are in the Peabody collections and on various other projects. And it's kind of very sort of fulfilling to recognize yourself as part of this collaborative group of people that all have this shared sort of academic background and academic lineage.
I mean, science is all about people primarily who are excited and curious about the questions that you can address. And in the case of paleontology, of course, that's about the history of life on the planet. And if you fund those people, you'll make all sorts of exciting discoveries, and we'll understand a lot more about where we come from, and more importantly now, I guess, where we're going, because with environmental change, we can look at the sorts of issues that have bedeviled organisms in the past.